All right, let's continue our discussion of thermodynamic analysis of equilibria involving mixtures. Okay, and so previously we said that the key to understanding equilibrium is the chemical potential mu, and we said that the chemical potential is just the partial derivative of the Gibbs energy with respect to number of moles at constant temperature and pressure. And if you're dealing with mixtures, then the chemical potential of, let's say, component A of your mixture would be partial derivative of G with respect to moles of A at constant temperature, pressure, and you also have to hold the number of moles of the other components of your mixture constant for that in that partial derivative. Now, unfortunately, there is no absolute scale for Gibbs energy. But fortunately, we're only interested in changes in chemical potential. And since we're only interested in changes, it's actually more convenient to express the chemical potential in terms of quantities that we can actually measure in the lab. And so we can define a quantity called an activity as a measure of the difference between the chemical potential of a species in a system and its chemical potential in some reference or standard state. So in other words, the chemical potential of, let's say, a particular species in a system minus its chemical potential, its some standard state, some reference state, would be, we define it to be equal to RT times the natural log of the activity. So in other words, we define activity as e to the mu minus mu naught over RT. Okay, as we shall see in the following discussion, in the following slides, we can relate activity to things that we can actually measure in the lab. All right, so consider an ideal gas mixture containing species A with a partial pressure of P sub A at constant temperature and pressure. So P sub A is part of a mixture, so the total pressure must be higher than P sub A. Okay, P sub A is a partial pressure of component A. Now, what would be the difference between the chemical potential of A in this mixture and its chemical potential in what we would call the standard state? Now, the standard state for gases, ideal gas, would be the case where your gas at the same temperature is at a pressure equal to P naught. So mu A is equal to mu at P equals P naught. Mu sub A at P. Mu sub A naught would be mu sub A at P equals P naught. All right. So the difference between those two would just be the total change in the chemical potential if you start off with, imagine starting with a pure sample of A at pressure P naught. So that's your A at your standard state. Okay, lower the pressure of that pure A, okay, to P sub A, the partial pressure you want, and then imagine introducing some other gas molecules in there so that it will now be part of a mixture with a total pressure of P. Okay, so this is pressure of P total here. But the partial pressure of A will remain P sub A in that mixture because it's an ideal gas mixture. A will not be interacting with the other gas molecules that you introduce. All right, so the total change in the chemical potential in going from here to here would be the difference in the chemical potential of A in the mixture and its chemical potential when it is pure and at 1 bar pressure, standard pressure. Well, delta U, change in U for delta mu, the change in chemical potential for the first step, step 1 right here. Delta mu for step 1 would just be RT. We've seen this before. This is just change in the molar Gibbs energy. So RT ln P sub A over P naught. The change in chemical potential for step 2 will just be equal to 0. Why? Because it's an ideal gas mixture. A really doesn't care about the presence of the other gases in there. It's an ideal gas mixture. So the first step, delta mu for the first step is RT ln PA over P naught. Delta mu for the second step is 0. Okay, let's clean this up a little bit. So I can rewrite mu sub A for the mixture must be, I'm going to move this over to the right, so it's just chemical potential of A, pure A, at 1 bar pressure, that's a standard state chemical potential, plus RT ln PA over P naught. I'm just rearranging the equation. Now, like I said, pure A at P naught, we take that as our standard state, then you can see that our activity is really nothing more than P sub A over P naught. Why? If you recall, we said chemical potential of A is equal to chemical potential of A in some reference state, right, which is, in this case, would be pure A at P naught, plus RT ln of the activity of A in that mixture. So the activity of A in that mixture has to be PA over P naught. So you can see here, we define a quantity called activity, which is something we can easily measure in the lab. In the case of an ideal gas, that would be the partial pressure of an ideal gas. Okay, so the activity is PA over P naught, regardless of what that pressure is in your system. Right. So activity for an ideal gas is just PA over P naught. What if the total pressure happens to be equal to P naught? Then what do we get? We get, then our activity will be equal to, which is PA over P naught, will now be equal to PA over P. And if you recall, what is PA over P for an ideal gas? Partial pressure of A over the total pressure is moles of A, RT over V, divided by total moles times RT over V. So RT over V cancels out. That's just moles of A over total moles. That's just the mole fraction. For gases, it's often convenient to use letter Y for mole fraction, because later when we deal with liquid and vapor in equilibria, we are going to use the letter X for mole fractions in the liquid and Y for mole fractions in the gas. Okay, so we can then say then the activity of A, okay, activity of an ideal gas component, a mixture of an ideal gas component at standard pressure will be whatever its mole fraction is. So in other words, we're going to say mu sub A is equal to mu sub A naught plus RT ln Y sub A. In general, the activity is PA over P naught, partial pressure divided by P naught. Note that activity is a unitless quantity, right? It's a ratio of two pressures. Now, of course, if A is not ideal, then the activity will just be, okay, fugacity divided by P naught. We talked about fugacity earlier. All right. Okay. All right, so let's look at this example right here. What is the activity of neon in a gas mixture containing 0.2 moles of neon and 0.8 moles of helium at 298 Kelvin, 2 bar pressure, assuming you have an ideal mixture? Then activity, we said, is just pressure, or partial pressure of neon over P naught. And partial pressure of neon in a mixture will just be mole fraction of neon times the total pressure. And so you divide that by P naught, that will give you your mole fraction, your activity for neon. So in this case, it's going to be 0.200 times, oops, we need mole fraction, right? So mole fraction of neon is just 0.200 over the total moles, which is 0.200 plus 0.800. That's equal to 0.200. That's your mole fraction. Okay, so our activity then would just be equal to 0.800 times the total pressure, which is 2.00 bar, divided by P naught, which is 1 bar. Okay, so bar cancels out. Activity, as we said, is a unitless quantity, and in this case, what's 0.8 times 2? That's 1.60. That's it, unitless. Okay, so activity in this case for neon is 1.6. What about, let's take a look now at volatile liquids. The strategy for determining activities for volatile liquids is as follows. First, you consider a liquid mixture in equilibrium with the gas. Okay, so let's say you have a liquid mixture containing A. So you have a liquid right here. Part of that liquid is A, component A plus others. Okay, and then you have A in equilibrium with the gas. So in the vapor phase, you have an enclosed container. You have A in a liquid in equilibrium with the gas. Now, the chemical potential of any volatile component of the liquid, so A in this case would be an example of what you would call a volatile component. It's also present in the gas phase. So the chemical potential of any volatile component of the liquid will be equal to its chemical potential in the gas phase. So typically we're going to be dealing with cases where the vapors pressure is low enough, so we're just going to assume our vapor is ideal. So the chemical potential of A in the liquid must be equal to its chemical potential in the gas. Well, we already have a formula for the chemical potential of a gas. It's just mu A naught plus RT ln PA over P naught. We just talked about that earlier. So the activity of the liquid then can be determined by comparing the vapor pressure, okay, the pressure of the gas, of A in the gas, to the liquid's standard state. Let's elaborate on that. Exactly what do we mean by that? Well, if you have a pure liquid in equilibrium, imagine you have a pure liquid, okay? Imagine your standard state is a pure liquid. Your standard state for comparison purposes is a pure liquid, so this is pure A, in equilibrium with gas at pressure P sub A star. Okay, we're putting a star here to indicate that that gas is pure. Okay, it's in equilibrium with pure A. So mu A star, the chemical potential of A in the pure liquid, is equal to its chemical potential in the gas phase, and so that's equal to mu naught plus RT ln partial pressure of A in the gas phase is PA star, because that's the partial pressure of A in equilibrium with the liquid, over P naught. Okay, so based on this, we can say then that mu naught, how is mu naught related to chemical potential of the pure liquid? This is our standard state chemical potential. It's going to be equal to mu A star plus minus, okay, minus RT ln PA star over P naught. Okay, all I did was solve for mu naught here, so I move this thing over to the left side. Subtract that from mu A star. All right, now consider this time the actual liquid, which is a mixture. So you have now a case where you have A is part of a mixture. So A is your liquid right here, which consists of A plus other stuff. Okay, and then you have A in the gas. And this time, the partial pressure of A is not going to be equal to PA star. We're just going to call it P sub A. Whatever it is, we can measure it. Okay, PA star we can also measure. So you can say then that the chemical potential of A in the mixture, in the liquid mixture, must be equal to its chemical potential in the gas at equilibrium. That's the condition for equilibrium between phases, right? But we know what mu A is for the gas. It's mu naught plus RT ln PA over P naught. All right, so what do we do now? We have chemical potential of A in the mixture, which is this one, is equal to mu naught, which we identified above. Okay, here's mu naught right here. Oops. This is our mu naught. We're going to substitute mu naught there. So plus RT ln PA over P naught. So here's what we did. We have mu naught is mu A star minus RT ln PA star over P naught. So that's our mu naught. plus RT ln PA over P naught. Okay, so this is this one right here. Okay, let's simplify this expression now. If you simplify this expression, you can combine these two terms right here. Okay, so what we have now is mu A star, this is mu A star, and these two, that becomes negative RT ln PA star over P naught plus RT ln of PA over P naught. Okay, so I can factor out RT. Okay, and I'm going to have negative ln of PA star over P naught plus ln of PA over P naught. So this is like ln x minus ln y, right? So ln of x minus ln of y is just ln of x over y. So that means I can rewrite this thing as RT times ln of x, this is my x right here, PA over P naught over, this is my y right here, PA star over P naught. Okay, and I can simplify that, and that's equal to RT natural log of, oops, P naught cancels out, that's PA over PA star. Okay, so that's RT ln PA over PA star. And this is the expression that we have over here. Right. So let's compare that to our defining equation for activities. What did we say an activity was? So measure the difference between the chemical potential of whatever species you're interested in whatever system you're dealing with, and its chemical potential, the difference between that and its chemical potential in the standard state. So our standard state is a liquid, a pure liquid. So chemical potential of the pure liquid is mu A star. The difference between these two is RT ln activity. Okay, so we can readily identify the activity is nothing more than PA over PA star. All right, so our activity for a liquid that's part of a mixture, a volatile liquid, would be PA over PA star. All right, so what would be the activity of a pure liquid? Then that would be 1, because then pure liquid PA would be PA star. So in other words, the activity of a standard state, something in its standard state, would be equal to 1, because because you'll have, if your chemical potentials are the same, then natural log of A has to be 0. So ln of A is 0, then its activity must be equal to 1. So a pure liquid, its activity is going to be equal to 1. All right, so let's look at this problem right here. Let's say at 298 Kelvin, the vapor pressure of pure liquid A is found to be 0.20 bar. So that means that's PA star. Now, you have a mixture where the mole fraction of A is 0.9, and the partial pressure of A in the vapor is found to be 0.16 bar. So you have a mixture, and mole fraction of A here is 0.9, so it's got something else besides A in the liquid, right? And your gas, your PA here is given to be 0.16 bar. So piece of A in equilibrium with our mixture is 0.16 bar. So what's the activity of A in our liquid phase? Activity of A is just equal to piece of A over piece of A star. So it's going to be 0.16 bar divided by 0.20 bar. And that gives us 0.16 over 0.20, 0.80. That would be the activity of our liquid, of A in our liquid. Okay. Now, so we said that for a volatile component of a liquid mixture, if you're using the pure liquid as your standard state, the activity is PA over PA star. Now, you've seen an equation similar to this in your earlier courses. It's called Raoult's law, and when you talk about colligative properties in your freshman chemistry, it was empirically found that as your mole fraction approaches 1, so in other words, for very dilute solutions, the mole fraction of the solvent approaches 1, then PA over PA star is found to be equal to the mole fraction of A in the liquid. In other words, what is this saying? As the mole fraction of the liquid approaches 1, so the more dilute your solution is, your activity will just approach the value of the mole fraction. Okay? And if it's pure, eventually your mole fraction is just going to approach the value of 1. So at very low mole fractions, your activity will just be equal to the mole fraction. Okay? So for very dilute solution, the activity of the solvent will essentially be equal to the mole fraction of the solvent. Now, if you have a solution that obeys Raoult's law under all circumstances, okay? In other words, if XA happens to be, okay, the activity of A, which is, in other words, if PA over PA star happens to be equal to the mole fraction, then you say you have an ideal solution. So we define an ideal solution as one that obeys Raoult's law. So what would be the activity of component A of an ideal liquid mixture? Then the activity would just be equal to the mole fraction. Okay? If it's ideal. That's the definition. Now, real solutions may deviate from Raoult's law. So if you measure the activity by measuring PA and PA star, you might find that that's not equal to X of A. So what we do is we introduce a correction factor there, gamma. And that gamma right here is what we will call your activity coefficient. So that's our attempt to correct for non-ideal behavior. We introduce that correction factor, gamma. Okay. Now, the basis for that is basically the same thing as what we did before when we talked about fugacity as a deviation from ideal behavior for gases. If you remember, okay, when we talked about ideal gases, real gases, we said chemical potential of a real gas is equal to its chemical potential if it were ideal, okay, plus RT, ln fugacity, of course, RT, ln gamma, right? Ln gamma, right? And mu ideal, we said, was mu naught plus RT, ln P over P naught. That's our mu ideal plus RT, ln gamma. So, same idea here, okay? Instead, our mu ideal in this case would be mu star plus RT ln mole fraction of A. And so if you have a real component, real solvent, which deviates from ideal behavior, then it's equal to mu ideal, which is mu star plus RT ln XA plus RT ln gamma. Okay, so if gamma is 1, your solution is behaving ideally. You say it obeys Raoult's law, and you can interpret gamma less than 1 and gamma greater than 1. The 1 as deviations from ideal behavior. Okay? See, if you combine these two, that gives you RT ln gamma times X of A. So let's look at this example right here to illustrate that concept. The vapor pressure of a liquid, pure liquid A, let's say is 0.2 bars. It's the same problem as before. So, and suppose you have a mixture where the mole fraction of A is 0.9. So you have your A here, mole fraction of A is 0.9. You have a mixture of A where the mole fraction of and something else, and mole fraction of A is 0.1. And the vapor pressure of A, partial pressure of A in the vapor is found to be 0.16 bar. Okay? Now, if it was pure, your vapor pressure of A, so PA star, is found to be 0.20 bar. Same problem we had earlier. Calculate the activity coefficient and see if it's, assuming the vapor is ideal, see if our liquid is ideal. All right, so we say then that activity is equal to, we measured this earlier, is PA over PA star. We calculated this earlier. It's 0.16 over 0.20, right? Bar, so that's going to be 0.80. That's our activity. But what's our mole fraction? Our mole fraction is 0.9. 0.90. So we say our activity is gamma times our mole fraction. So our activity coefficient gamma is equal to the activity divided by the mole fraction. So our activity is 0.8. Our mole fraction is 0.9. So our activity coefficient is 0.8 divided by 0.9 is going to be 0.89. Okay, so that's how you can measure the activity coefficient for your solvent. You base it on vapor pressure measurements. All right. Now, how do we explain Raoult's law? Why is the vapor pressure lowered when a liquid is contaminated? That's basically what it's saying, right? Piece of A, a volatile component A, is equal to its pure vapor pressure times the mole fraction of A. So since X of A is a number less than 1, the actual pressure, partial pressure, above a mixture, above a contaminated liquid A would be less than what it would be if it was pure. Well, at the molecular level, how can we explain that? Because then that will allow us to explain deviations from ideal behavior. So let's look at the ideal case here. Okay, see what the molecular level explanation for that is. So if you were to look at liquid A, okay, in equilibrium with gaseous A. So you have A in the gas phase right here, right? Going back, and let's say you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that's liquid pure A in equilibrium with gaseous A. So at equilibrium, the rate at which your molecules will take off and go into the gas phase is equal to the rate at which your molecules will land back onto the liquid and go back to the liquid phase. What will happen if our liquid is contaminated? You can imagine that the takeoff sites for A is going to be blocked by the contaminant. So let's say our mole fraction of A is only 0.8. What will happen? Then of these 10 molecules that I've drawn up here, 2 will now be a contaminant, right? So A is now blocked. The takeoff sites, some of the takeoff sites are now blocked by the contaminant. So now, but the landing sites remains the same, okay? All of these, there's no restriction on where the gas molecules can land back on their way back to the liquid. So what happens is the ability of A to escape the liquid is lowered. So you say the chemical potential of A has been lowered. Its ability to disappear from the liquid has been lowered. Okay? So the chemical potential of A in the liquid is lowered. And so the chemical potential of A in the vapor has to go down eventually. And the way it goes down is by lowering the pressure. So eventually you'll have fewer gas molecules in the vapor when equilibrium is reestablished. So that is the interpretation of ideal behavior. Now, so that's ideal behavior. When do we expect non-ideal behavior? When do we expect deviation from this ideal behavior? Well, something like, let's say one of your contaminants are big, okay? So compared to your A molecules, then you can expect that they will be blocking more of the takeoff sites. Or what if your contaminant strongly attracts the A molecules around it? There's very strong attractions between the contaminants and the A molecules. Again, that's going to have, you expect to see a negative deviation from Raoult's law. So when do you expect ideal behavior? If you're mixing two things that have very similar structure, for example, benzene and toluene. Okay, if you recall, benzene is this, and toluene is this. So very similar structures, very similar size, very similar interactions. Solid-solid interactions and solvent-solvent interactions are very similar, and solid-solid, solid-solvent, and solvent-solvent interactions are very similar, then you would expect to see ideal behavior. All right. How can we explain Raoult's law using this equation right here? Remember, dg is equal to minus s dt plus v dp. Okay? So d mu is negative s bar dt plus v bar dp. Right? So what would happen if we were to plot mu versus temperature versus pressure at constant T? That would be what? Versus pressure. So partial of mu with respect to pressure at constant T is just V bar, right? So what would be the molar volume of a liquid compared to a gas? V bar for a liquid is going to be much smaller than V bar for a gas. So what would that plot look like? Remember, this derivative is just the slope, right? So the gas is going to have a much steeper slope, right, than a liquid. So a liquid would have maybe a slope that looks like this. Right? So what happens to, okay, so this is your gas, and this one right here is your liquid. What happens when you contaminate your liquid? And now plot mu versus P. Okay, that should be mu versus P at constant T. So the chemical potential of your liquid will now be lowered by an amount equal to RT ln X. Why lowered? Because X, the mole fraction, is going to be a number less than 1, between 0 and 1, right? So ln of X would be a negative number. So mu star plus a negative number, the chemical potential in the liquid will be lowered when it's contaminated. So your liquid will now have a lower chemical potential. And so effectively what happens is, okay, what do you have, what does this intersection right here mean? That's when the chemical potential of the liquid and the gas are equal, right? So this is your vapor pressure right here of your pure liquid. So this is right here, that's PA star. And what happens to that intersection between the two curves? Right here, this one you have your PA. So you have vapor pressure lowering when you contaminate the liquid. All right, so now let's take a look at what happens to G, V, S, and H when we mix two liquids and they form an ideal mixture. Okay, so if A is a component of your mixture, then its chemical potential in the mixture is just equal to its chemical potential. If it were pure, that's a standard say chemical potential plus RT ln X of A. Remember we said the activity of a component of a liquid mixture is equal to its mole fraction if it's behaving ideally. okay, if it obeys Raoult's law. All right, so if you recall, mu sub A is just the partial molar gives energy, okay? Oops, sorry. There should be a bar over here. This is G bar sub A. So it's partial derivative of G with respect to moles of A holding temperature, pressure, and all the other moles of the moles of all the other components constant. So that's the definition of chemical potential. So let's calculate delta G, delta V, delta S, and delta H for mixing N sub A moles of A and N sub B moles of B at constant temperature and pressure. Delta G is easy because delta G will just be 1. Okay, it's just, remember your G, okay, will just be equal to moles of A, G bar of A, plus moles of B, G bar of B, right? Partial molar quantities, if you remember. That's the expression. Okay, so it's just going to be N sub A, mu sub A, plus N sub B, mu sub B. So if you want to get delta G, you want N sub A times mu sub A in the mixture minus N sub A times mu sub A if it were in the pure. Okay, so what you actually have here, okay, let me just put these two together. This N sub A, mu sub A in the mixture plus N sub A, mu sub B in the mixture, that is your G for the mixture. Okay, so that's G for the mixture. And then G for the pure stuff would be mu sub A star, N sub A times mu sub A star plus N sub B times mu sub B star. So that's your delta G. All right. Now, I've rearranged that equation, that expression to this because now I can put these two together. Mu sub the difference between the chemical potential of A in the mixture and its chemical potential in the pure liquid is just RT ln X of A. And the difference between the chemical potential of B in the mixture and its chemical potential when it's pure is just RT ln X of B. Okay? So what the expression we get then is here. It's N sub A times RT ln XA plus N sub B RT ln XB. So that's the delta G for mixing if you have an ideal mixture. All right? So why should that be less than 0? At a given temperature and pressure, constant temperature and pressure, that's your delta G. Why should that be less than 0? Well, I can remember XB and XA are mole fractions. So the natural log of a mole fraction is a natural log of a number less than 1. So that's going to be a negative number. So you have a negative number here. And moles are positive, R is positive, T is positive. So the natural logs are negative. So the entire expression will add up to a negative number. In other words, the Gibbs free energy change for ideal mixing is negative. So in other words, if two components form an ideal mixture, then the mixing of the two is a spontaneous process. Delta G is less than 0. Okay? What about delta V? How are we going to solve for delta V? Change in volume. How can we tell? How can we determine delta V? Look at dG equals minus S dt plus V dt. What's volume here? Volume is just partial of G with respect to pressure holding temperature constant, right? So delta V would just be partial of delta G with respect to pressure holding temperature constant. Why is that? Well, think of it this way. Let's see. Delta V is just V final minus V initial, right? And V final is partial of G final with respect to pressure at constant T minus partial of G initial with respect to pressure at constant T. So you can just combine the two, and that will give you partial of delta G with respect to P at constant T. All right, so if we have um, delta V is expressed that way, what do we get? So delta V is partial of delta G with respect to pressure at constant G. Do you see any pressure dependency? None. So delta V would just be equal to 0. Okay. What does delta V equal to 0 means? Final volume equals initial volume, so that means we say volumes are additive. Okay, the volumes will just add up if you have an ideal mixture. Now, if you don't have an ideal mixture, then your volumes are not going to add up. So you may not, so like 10 mils and 10 mils of two different liquids might give you less than 20 mils, or might give you more than 20 mils. Of course, you should be able to do a molecular interpretation of that. What would it mean if the total volumes don't add up, is less than the individual volumes? Then that would mean you're looking at strong solute-solvent interactions as opposed to interactions amongst the solid molecules and amongst the solvent molecules. Okay? And if delta V is positive, then that means the solute-solvent interactions are weaker than the individual solute-solute and solvent-solvent interactions. Okay. What about delta S? Okay, so delta S is going to be a positive number. Okay, and why would that be? Well, here's S right here. So S is negative of the partial derivative of G with respect to T. Okay, there's T right there, holding pressure constant. So delta S would be the negative of the partial derivative of delta G with respect to temperature and constant pressure. Okay, so let's take the derivative with respect to temperature at constant pressure. This whole thing is just constant. This whole thing is just constant. So derivative with respect to T would just be N sub A R ln xa plus N sub B R ln xb. Okay, but you have to put a negative in front of this. Okay, there's a negative right there. So delta S mixing is negative of N sub A R ln x sub A plus N sub B R ln x sub B. And why would that be a positive number? Well, ln, remember we said natural log of a mole fraction is a negative number. So negative plus negative, the whole thing inside the bracket is negative, but you have a negative term outside, so that's a positive delta S. Okay. What about delta H? Delta H is going to be equal to 0. Why? Here's one way you can do it. You just say that delta G equals delta H minus T delta S. Okay. And so delta H would just be equal to delta G plus T delta S. And if you did that, what do you get? Delta G is N sub A RT ln XA plus N sub B RT ln XB. That's your delta G. Plus delta T times delta S, which is negative N sub A RT ln XA minus N sub B, there's no T there. Negative N sub A R ln XA minus N sub B R ln XB. But once you multiply that by the temperature, you can see that that will just give you 0. Okay? So delta H is just equal to 0. Another way of thinking about it is, look, if you look at this one right here, this is really nothing more than negative delta G over T. Okay. So that's another way of looking at it. So you can say that delta H equals delta G plus T times negative delta G over T. T cancels out. Delta H is 0. So what kind of experiments can you do to determine if a mixture is ideal? We've already mentioned mixing the volumes. See if the volumes add up. Volumes are additive. That's a sign of ideal mixing. Another experiment you can do is you can do delta H of mixing. You can mix the two liquids. If delta H is 0, what do you expect? At constant temperature, at constant pressure, then you would expect no temperature change, right? If you mix the two. If you were to delta T for mixing, okay? If you were to mix the two liquids and the temperature went up, what does that mean? Delta H is negative. You have an exothermic mixing process. You would see deviations from ideal behavior. Okay? You're looking at an exothermic process would mean what? At the molecular level, you're seeing a lowering in the potential energy of your system. So the kinetic energy of your system increases, and so momentarily it becomes warmer than the surroundings. Heat goes out of your system. You have an exothermic mixing process. So a lowering of potential energy simply means that in the mixture you have stronger attractive forces. You're dealing with stronger attractive forces as opposed to the separated components.